Welcome to Empowered Learning. This is the second video in the video series on work and modeling this concept by using definite integrals. So in the first video, we went through some of the basic theory involved in coming up with our basic formula for work, and I'll just go ahead and write that again. So we know work in general is just going to be the definite integral of our force function f of x from x equals a to x equals b. That's pretty much it. The part that's a little bit complicated, depending upon what type of problem that you're dealing with, is how to actually model your force function f of x. And so in this video, we're going to continue on with examples that are not worked out, so you can see how I would work them out from scratch here. But in doing that, we're going to look at some different types of problems as well. So these are not going to be necessarily problems that are exactly like the ones that we covered in the first video. Okay, and so I purposely did this so that we can get a good variety here. So with this first problem, this is a classic problem where you have some kind of scale. In this case, it's a bathroom scale, and we assume that this bathroom scale is compressed at a 12/100ths of an inch when a 120-pound person stands on it. So just from looking at this, we know that this is a distance and this is a force. Okay, and so if we assume that the scale behaves like a spring that follows Hooke's law, so that means that our force is going to be directly proportional to the distance that the spring in this case is going to be compressed instead of stretched. Then we want to know how much does someone who compresses the spring by 5/100ths of an inch actually weigh. Okay, and then we want to know how much work is going to be done in compressing the spring for the person who's going to weigh however much we're going to find out here. Okay. All right, so the first thing here is we know that when a 120-pound person is on this scale, basically, or on this spring, basically, we know that the spring is going to be compressed by 12/100ths of an inch. So look here, just like that. And so from here, we can just basically divide 120 by 0.12, and that's going to be what our value of K is going to be. Okay. Put this another way here. If I move the decimal place over 2 in the denominator, then I'll have to do the same thing in the numerator. Okay. And so with this, this just essentially says here that our spring constant is going to be 1,000, and because 120 was in pounds and 0.12 is going to be in inches, this is going to be 1,000 pounds per inch. Okay, so that will be what our spring constant is. So we'll take that and we'll say, since K is going to be 1,000 pounds per inch, then that means that our function here, we'll call it big F of x, is just going to be 1,000 times x. And this unit here will be in pounds. And we know that because x was given to us in inches. And if we have pounds per inch, so I'll write it here, pounds per inch times inches, the inches reduced to 1 and we're just left with pounds. So now that we have our force function here, the work that's going to be done, actually let's figure out how much the person weighs that does this part first. So yep, I'm trying to get to part 2 and haven't finished part 1 yet. So now that we have this, then we know that if this person compresses the scale by 5/100ths of an inch, then that means that here, just do this, and so basically that's going to be 5% of 1,000 here. And so this will just end up being 50 pounds once we actually multiply all that out. Because 5% of 1,000 is just going to be 50. Okay. So now that we've answered that question, so I'll call this like my part 1 here. So part 2 now is saying, well, how much work is done in this particular situation? Okay. Well, we know work is just going to be the integral, and here we're compressing the scale by 5/100ths, so it's just going to be 0 to 0.5, and of course this will be f of x dx, and of course in this case function here is going to be 1000x dx. Okay. All right, so one thing I do want to make sure that you understand before we complete this problem here is that we do actually have to use the function 1000x instead of just using 50 here. And I say that because we know that in doing the work is not just a force. The work is the force times the actual distance there. Okay. And so we're going to check this out to make sure that everything works out the way that it should. But because of the fact that we're talking about compressing the spring, we have to take into account all the little, I guess the small increments of the spring going down from 0 inches down to 0.05 of an inch. The little minuscule amounts of work that's done all the way down, and then we're summing all those up. And so to do that, that's why we have to use this formula here, okay? Because that kind of encompasses all of that without us having to specifically write out, n, which is infinitely many of these little small increments of x that we actually, tally up all the little small works that we do. All right, so here, if we just go ahead and factor out the 1000, and then we take the antiderivative of x, which would just be x squared over 2, and evaluate that from 0 to 0.5. Then from there, it's just a matter of doing a little arithmetic, and we will get our answer here. So we know 2 goes in 1,500 times. And with what's left, which is x squared, if we go ahead and plug in 0.05 and square that, minus 0, we square that. And then we essentially just have 500 times 0.05 squared. Okay. And so from here, I know 5/100ths, we can just look at it like this. And of course, since that's squared, I can write that twice. And I'm just trying to do this without, having a calculator here. If I have it like this, then of course, 100 goes into 500 5 times. And here we know 5 goes into 100 20 times. And so we got 5 times 5 times 20, which is going to be 4 times 5. And these 5s reduce to 1. And we got 5/4. And this work here, since our units were in pounds and our, the force was in pounds and our length was in inches, this would be 5/4 foot-pounds. If you wanted to express that as a decimal, that would be 1.25 foot-pounds. Okay. And so that would be your answer to how much work is actually done. All right, so for our second example, we have a rectangular tank that's shown here with its top at the ground level and this tank is used to catch runoff water. And we want to assume here that water is weighing 62.4 pounds per cubic foot. And so the first thing that we're asked to do here is to find out how much work does it take to empty the tank by pumping the water back to ground level, okay? So we assume that the tank is full and we want to pump all the water out. So to figure out how much work it's going to take to pump out all the water, the approach that we want to take here is to figure out how much work is it going to take to pump out a random slice of water out of the tank. Some people may call it a slab. I like to call it a slice. Okay. So to do that, we need to model what is going to be the work in getting this one random slab that we see here. What is the work that it's going to take to get that random slab pushed back up to the top and out? Okay. So we're going to model this, say, work for slice. A slice of water. Yeah, let's do it like this. Okay. Now, first thing that we know is that water is weighing 62.4 pounds. Okay. So we know that we're going to use that. In general, we know that work is just going to be force times distance. So we're going to have to model the force and then afterwards model the distance. Okay. So for the force end of things here, we know that we have this 62.4 pounds per cubic foot. And since we have that, we know that whatever else it is that we're going to multiply by here, the end result is going to have to be cubic feet. Okay. Now for the slice of water here, we see that one side of it is 6 feet. Another side of it is 18 feet. And that always stays the same there. So we're going to have 6 feet by 18 feet. Okay. Now, of course, the height of the slab here is going to be this delta y that you see here. So this is going to be delta y feet. And of course, feet times feet times feet gives us the cubic feet that we're looking for. Okay. So all of this models the force because, of course, cubic feet times pounds per cubic feet is just going to give us pounds. Okay. Now we need to model this distance. And so notice that no matter where the slab of water is, to get to the top of the tank here is going to have to travel y feet to do it. Okay. So in this case, we know that this distance here is going to be y feet. Okay. So in looking at that, if I come down here again and say work for slice of water, then all I'm going to do is take the 62.4, multiply it times 6, multiply it times the 18, and I'm just going to put 62.4 here. I know 6 times 18 is 108, so we're going to do that. And I know that I have this delta y here and I have this y, so I'm just going to say y times delta y here. And that's going to be the work that's going to be involved in taking that one slice of water and pumping it out of that tank. Okay. Now, the goal here, I'm going to rename this W sub I. The goal here is for me to take all of these slices here and have an infinite many of them that I could stuff in this tank from the bottom of the tank to the top of the tank and add up all of the work that goes into taking each one of those infinitely many slices of water and basically pumping it out of the tank. So here, what I'm trying to get at is that the total work here, which we call W, is just going to be the summation of all of these W sub i's, okay? And to be more specific about it, where the number of slices that I'm going to have is going to go towards infinity, okay? And so how I would write that is the limit as n approaches infinity of, and then I would have summation here from I equals 1 to n. And of course, my W sub I is just all of this business here. So it's 62.4 times 108 times Y delta Y. Okay. And so here, if we look at this by definition, we know whenever we do the limit of the infinite sum, or the limit of this Riemann sum here as n approaches infinity, which ends up being an infinite sum, we know that that by definition is basically an infinite sum, which is going to be an integral. Okay, so all that's going to come out to be is integral, and we're going to do it from the bottom of the tank to the top of the tank. And so the distance that it would have to travel here will just go from 0 to 40. That would make it real simple here. For some reason I can't draw that 4 today. So let's try that again. All right, so let's try this one more time. Okay, so got 40 there. And then this is going to be the 62.4 times 108. And of course, once we do the integral here, this delta y here will actually turn into a dy. So this is going to be y dy like that. And so now that we have a nice formula for the work, that's going to take all those random slices of water, all infinitely many of them, and kind of total them up to see what the total work's going to be. This is just another way of saying that. And so now we can just do the calculus here. And we know that the antiderivative of y is just going to be y squared divided by 2. And that's going to be evaluated from 0 to 40. And here this would be just 62 times, and this should be 54 here, because I know 2 will go into 108 54 times. And here I will take 40, and I will square that, minus 0, and square that. And so from here, I mean, at this point, we're pretty much done. We know that 0 squared is just 0. We know that 40 squared is just going to be 1,600. So we would just have this 62.4 times 54 times 1,600. And so now the number that we get here is 539,1360. So it looks like 5,391,360. And this would be in foot-pounds. Okay, so this would be our actual amount of work that it would take to take this tank here, and with it being full, pump all the water out of it where the water weighs this much. Okay. All right, so we have various parts of this question here. So now that we know what the work is, we're going to play around with this to try to see if we can sort of estimate how long it's going to take for us to actually pump out the water. Okay, So let's go to part 2 of this. And so part 2 says, if the water is pumped to ground level with a 4/11, or basically a 200 foot-pound per second motor, then how long will it take to empty the tank? And we want to figure that out to the nearest minute. Okay, so we want a time to empty tank. So one thing that we do know is that we know the work that's going to be done. Work done to empty tank. We already know this. And remember, we have this in foot-pounds. Okay. We also know that the rate of work for the actual pump that we're going to use, or this motor that we're going to use in our pump, is going to be 200 foot-pounds per second. So if I have foot-pound and I divide that by, well, I'm putting pound-foot, but this should be foot-pound. So I'm going to write it like that. Let me fix this too. Yeah, because most people say foot-pounds. All right, so if I have foot-pounds and then I divide this by foot-pounds per second, and this hyphen here really means multiplication. It is not subtraction. And I'm just going to erase it and put multiplication there just so that this is not being confused for anything. So if we have it like this, then of course these foot-pounds here will reduce to 1, and 1 divided by 1 divided by seconds is just actually going to be seconds. So my point here is that if I take the work done that we found in part 1 and I divide this by 200 foot-pounds per second, what I'm going to get is my answer in seconds. Okay. Now, what I really want is my answer in minutes. And so since I'm going to get my answer in seconds, I know that 60 seconds here is actually going to equal 1 minute. Okay. So because of that, what I have here is going to be in seconds. I'm going to need to divide everything that I have here by 60 seconds. And dividing this fraction by 60 seconds is the same as multiplying the denominator by 60 seconds. Okay. And so with that, once I'm done with all this, then the unit that I'm going to get left here is just minutes. Okay. So if we put in the numbers that we need here, so we have this, we have foot-pounds here, and of course seconds and seconds are going to go away there. We're just going to have minute here. We're going to have 200, and I'm just going to write everything here just to make sure. Second, and then this is going to be 60. All right, so I had to fix this pen here. So we know that we're going to have 60 here, and this is going to be, it's really going to be seconds per minute, like this. So we handle all the units here. Of course, the foot-pounds and the foot-pounds here will reduce to 1. The seconds and the seconds will reduce to 1. And all I will have left is 1 divided by 1 divided by minutes, which is just going to be minutes. And I would just take this number, 5,391,360, and basically divide it by 200 times 60. And I'll figure out what that is right quick. So if I do that, it's 200 times 60. Fat fingered something. All right, so that should be 449.28. Okay, so 449.28, and that's in minutes. And so since I wanted to round to the nearest minute, that's going to be approximately 449 minutes. Okay. And so if you're wondering what that is, it's going to be roughly about 7.5 hours. So a lot of time. Okay, so we figured that part out. So now let's look at part 3 of this example. So part 3 of the example, it says to show that the pump in part 2 will lower the water level 20 feet. And that's basically saying it's going to get half of the water out of the tank, since the height of the tank was 40 feet. We want to show that basically half of the water will be out the tank during the first 112 minutes of pumping. Okay. All right. So to do that, the first thing that we want to do is go back and figure out, all right, well, how much work is it going to take for me to pump the first 20 feet of water out of the tank? Now, at first glance, you will probably think that, oh yeah, well, it should take half, okay? But the thing is, it actually doesn't work like that. The more water that you have in the tank, the harder it's going to be to get the water out the tank. So in other words, the first 20 feet, the first amount of water that lowers the amount of water, the first 20 feet, that first 20 feet of water is harder to get out than the last 20 feet, okay? So we need to figure out, how much that's going to be. So we have to go back to part 2 to see, hey, well, let's recall the actual model that we have for the work and use that given this new information here, okay? So I'm going to go back to example 2 here. Oh, sorry, not example 2, example 1 here, because that's where we modeled our work function. And so right here is what we need to use. Okay, so let me switch colors here. So this is what we need to use. What's different now is that instead of this being 40, we need to now have this at 20. Okay, so everything's going to be the same here, but now we're going to have 20 for the upper limit of integration versus 40. Okay. All right, so now that we got that together here, we know that the work done to empty first 20 feet out of tank, that is going to be integral from 0 to 20, the 62.4 times the 108 times y dy, okay? So again, pretty much everything else is the same, except for the fact that our upper limit of integration is now 20. So when we do this, the 62.4, 108 remains the same. We'll still have y squared divided by 2. This will go from 0 to 20. And of course, 2 goes into 108 54 times. Okay. And so here we'll have 62.4 times 54. And this will be 20 squared minus 0 squared, which essentially will be, pen is starting to act up again, 62.4 times 54 times 400, because 20 squared is 400. All right, and so in doing that here, I'm going to go ahead and calculate this. 62.4 times 54 times 400. That ends up being, looks like 1,347,800 840. And of course that will be foot-pounds. And I don't understand why I keep on writing pound-foot. Okay. And so now that we have that, we'll do the same thing that we did before. So time takes to pump out water, and we'll say with motor, in minutes. And so here we'll have the work that was done, so the 1,347,840, and we'll take that and basically multiply that times 200 times 60. And if you remember that from last time, that pretty much gave us what we needed to know. So if we take this amount divided by essentially 12,000, because that's what 200 times 60 is going to be, we see that we will roughly, well, we'll get 112.32 minutes, which is roughly 112 minutes. Okay, so that's how we get that particular answer. All right, so let's move on to part 4 of this example. All right, so part 4 of this example basically asks us to do the same thing as parts 1 and 2, but the weight or the weight density of the water is different. Okay, so if you remember in part 1, the weight density of the water was actually 62.4 pounds per cubic foot. But now we are decreasing that weight density sum. And so because of that, we are assuming that it's going to be a little bit quicker, that it's going to take a little bit less time for us to be able to pump the water out of the tank, and that the work required to pump all the water out of the tank is going to be a little bit less than what we had in parts 1 and 2 as well. Okay, so essentially here for our work, we're going to use the same exact outcome here. And that's just going to be this 62.28. That's the one thing that's going to change. The 108 that we got from the 6 feet times the 18 feet, that area is going to stay the same. And of course, we're going to have y dy here. All that stays the same. Okay. So if we do that, then of course we have 62.28 times 108, and we will take the antiderivative of y, evaluate it from 0 to 40, and I won't bore you with all the details on that. The answer just ends up being 5,380,992, and that would be foot-pounds. Okay, and of course, time to pump out water using the same motor, pump with the same motor that we had last time. We're just going to take the same amount of work here, and we're going to divide that by the 200 foot-pounds per second times 60 seconds to get it in minutes. And in the case, the denominator is essentially 12,000, and I'm just going to leave off the units here because we already know what the units are going to be. That's going to be in minutes. And of course, when we do that, the exact number that you'll get from your calculator here will be 448.416 minutes. And of course, that'll roughly round to 448 minutes. Okay. All right. So that is part 4 here is just what we did in part 1 and part 2. We just changed the number for the weight density of the water. And so part 5 here, I'll go ahead and scroll down to it. Part 5 is what is the answers to parts 1 and 2 whenever we have water that weighs a little bit more than what we had. Okay. And again, same kind of thing. So I'm not going to bore you with the details for that. The only thing that's changing here is that we put 62.52 pounds per cubic foot. And when we do that, our work will actually just end up being, let's try to get this to act right here. It'll be 5,401,728 foot-pounds. Okay. And for part two, if we look at the time that it's going to take to pump that water out with that amount of work, it's going to roughly be, I'll give you the exact number that you get and then give you the rounded number. So this will be 450.144 minutes. And of course, that just rounds roughly to 450 minutes. Okay. All right, so that concludes this particular example. We'll go ahead and move on to our next example. Okay, so for our next example, we're going to do something a little different than what we've done in the other two examples, in that this time we are not necessarily looking for work, but we are now looking for, well, we're going to talk about fluid force. And so the way that we model fluid force is going to be similar to, but not exactly the same as the way that we would model work. And so for this problem, we have end plates that look like isosceles triangles that are on some water trough that's shown here. And they're designed to withstand a fluid force of 5,000 pounds. Now, assuming that the density of water is 62.4 pounds per 62.4 pounds per cubic foot, how many cubic feet can the trough hold without exceeding this limitation? So in other words, we're trying to figure out with that constraint of the end plates of this water trough being able to take 5,000 pounds of fluid force of water, we need to know how high we can essentially fill up the water to where the amount that's in there at a certain height is going to be equal to 5,000 pounds of fluid pressure or below that. Okay. And the only information that we have other than the dimensions of the trough will be the fact that the water that we're actually pouring into the trough weighs 62.4 pounds per cubic foot. Okay. Now, to model this problem, we are going to have to look at force differently. And so I'm going to kind of sidetrack here for a second so that we can see how to look at force differently so that we can model this situation. All right, so just to kind of recap here, we have some end plates that kind of look like this isosceles triangle, okay? And I guess if I kind of turn it on its side here, I'm going to try to do the best I can to give you like a side view. What we are trying to do here is figure out if I have some forces acting on this particular triangular plate, I want to make sure that the force is not so much to where it's just going to make the trough break. And of course, I know that that force can't exceed 5,000 pounds. Okay. Now, when we think about force being over a certain area, you may not know this, but by definition, that is what pressure is. Okay. So if you think about, let's say your tire pressure, they always tell you that it's so many PSI or pounds per square inch. Okay. Pounds per square inch. And do you see how that is a force per unit length here? Okay. So in this particular problem, notice that we have the weight density of water. Okay, so we have this weight density of 62.4 pounds per cubic foot. Okay, and so since we know by definition pressure, and we'll just call this P, is going to be force divided by area, or force per unit area, and we could say it that way. Then we also know that force can be expressed as pressure times area. Okay. Now, if we think about the units for pressure, if we're going to keep pounds and feet here, so this should be pounds per square foot. Okay. And if we already have the weight density here, which is pounds per cubic foot, to get pounds per square foot, we are going to have to multiply by a unit length here, which is going to be feet. Okay. So we have that. Now, of course, for area itself, we know area is just going to be, since we're talking about feet, it'll be feet squared. And so, and I'm going to purposely separate this as feet times feet to kind of make my point here later on. Okay, so it'll be feet times feet. So if I call the weight density here W, then I gotta have its weight density be multiplied times something to get my pressure. And so if you think about it, this particular plate here, we're getting this this weight density of pounds per cubic foot is being applied all over this triangular plate. Now, putting that another way, the pressure of the water that's inside the trough is being applied to every single piece of this area for this end plate. Okay, so I'm saying that because in order to get this quantity for feet here, and I'm going to come over here and draw this, assuming that the trough cannot take the water being filled all the way up to the top, there's going to be some level that the water can be filled up to. Okay, and so let's say that this level is right here. Now, whatever level that is, just in general, we're going to say that that's a certain height from the bottom of the trough. Okay. Now, if we look back at our problem here, notice that we're kind of saying the same thing right here, meaning that there's going to be a certain height that we're going to call H that the water is not going to surpass. Okay. Now, again, we don't know if it's going to be able to reach up to 11 feet, but our thinking is that probably it won't be able to. So we need to be able to characterize the height of the water in the trough, knowing that it can't go above 11 feet. So noting that here, this unit feet here is actually going to come from the height of the water. And we're going to call that H. Okay. Now, of course, we know here we have to have some kind of area. And so because of the fact that we have to have some kind of area, and the area is going to be on this triangular plate here, let's assume, and I'm going to draw this little strip here. We're going to assume that this little strip that I'm drawing here, I'm going to try to, so that little strip that I'm drawing here will actually represent a piece or a slice of the total area of the actual end plate that we're looking at. And if I can actually model what's going on for one small slice of the area that I have for this, and of course, just like how we did with work, if I was to take that small slice of area, figure out what's going on with that, and then just add up an infinite amount of these small slices from the bottom of the trough to whatever the height of the water is, I could have a way to be able to fully model this force that's going on here by being able to essentially tell me what is this small slice of area going to be here. Okay. Now, in general, I know that if I can get, and I'm going to draw this again here, I know that for this small slice, if I can get this length going from here to here, if I can get that length, and I know that the height, if I'm looking at this in terms of y, okay, if I have a very small, minuscule amount of y, I could call that delta y. Then if I know length and I know that nice thickness there of that slice, that's all I need, okay? So coming back here, let's say I draw this little slice like this, okay? And here I'm also going to draw it. So let's just say this, and I'm really drawing like the volume here, but I just kind of want to show you how it would look on the other side. But what I'm really just focused on is this part here. So in noticing that this length that I have here, hold on, let me erase this. Since I have a way of knowing that's based upon this coordinate system here, I can actually quantify what is going to be, in this case, the value of x here and here, so that I can actually figure out what 2x actually is, okay? Now, of course, what I'm being told here is that from this point to this point, if I'm looking at this as a line, and that didn't go so hot, but yeah, if I'm looking at that as a line there, then of course y is equal to 11 over 6 times x. That will be that line. I could rewrite this to solve for x, and then after that multiply it times 2, and now I have what that actual length is, okay? So I have the length going from here to here, and I know that since I'm having a slice of that particular area that's on that end plate, the thickness of that slice would be delta y, okay? All right, so because of that, what we're going to say here is that we're going to, and this is the naming convention I'm going to use. I'm going to say L of y times dy, okay? Or let me do it this way. Yeah, let me not. We'll work our way to that later. So let's say I have a delta y here, and here let me say I have L of y sub I, because I'm talking about a specific one out of all. All right, so if we check out everything, we have pounds per cubic foot times feet, which would give us pounds per square feet, which is going to be pressure by definition. So we got pounds per square feet here. And if we multiply this times horizontal length, or the length across the triangular end plate at some height, that's going to be in feet, and delta y is going to be in some feet. And of course, we just get pounds, which is the actual force. So that is what we need. Now, in general here, there is a nice quick way to model fluid force. And it turns out to be that this force here going from A to B, this will be just the weight of whatever it is that that's applying the pressure times what we call strip depth. That times L sub y. So you kind of see here that that's going to be the length across the triangular plate here, in this case, at a given height h. And then this will be dy here. Now, how we get that is, of course, this weight and this height is just going to be what it is, right? But we know as for this portion here, for this area, we know that just for the area part, this could be summation of what this length will be at a particular y value times delta y. And ignoring the w and the h here, we would want to know what is going to be the behavior of this area here as the number of those little small slices of area that we consider grows to infinity. Okay, so we have something like this, then of course this will be WH, and then by definition this will be integral from some, I guess, x value or y value to another x value or y value. In this case it'll be y value. So I will switch this and make it go from C to D just to make it look different. And then here, this will just turn to L sub y. And by definition, this delta y will be dy. Okay. And so we see here that if I can figure out, or if I'm given what the weight density is, and I'm given this height for this, in general, it's just going to be some, specific constant y value. And then if I have that along with my horizontal length here, and delta y, then this ends up being the formula that we use to model fluid force. In general, we keep it like this because the context of the thing that we're trying to model fluid force on may be different. So it may not make sense to call this y value height right here, okay? So the main thing that I'm trying to get across here before I use this formula is to make sure that you understand how to use it, well, understand where it came from before you know how to use it. This part is the area that comes from here. And this part is your W times H, which is your weight density here. And really it's like your weight density times the area here. Sorry, not that. It's the weight density here times the strip depth, okay? And so the strip depth here is just going to be, in this case, whatever H is, but in general, it's just going to be how far down, or how much to the left, how much to the right. Something will be, in order for you to basically figure out what's going to be the pressure of the area that you're trying to cover, okay? And that's the main thing here, that this WH right here is taking care of the pressure part, okay? All right, so now that we understand how to model fluid force, we're going to go back to our problem, use it, and figure out the specifics of the weight density, the strip depth, the length of the horizontal strip that we're going to use, and then after that, we'll finish the problem. All right, so here we'll go ahead and write this formula again. Force, meaning fluid force in this case, it's going to be integral from, and we'll just say C to D, of, we'll say, weight density here. And I'm putting weight density here because we're talking about volume of water. But if the problem gave you something like what is the pounds per square foot, if it gave you that particular unit, then you would have to use that and readjust the way that you model this problem. Okay. All right. So we have the weight density here times what we're going to call the strip depth. And that's going to be just the small strip of area that we're going to consider, or slice of area that we're going to consider. And then this is going to be times L sub y times dy, okay? And where your L sub y is going to be the length of horizontal strip in this case. And we already know from what we saw up here that that length is going to be 2x. We're just needing to be able to define 2x in terms of y here. All right, so now that we have all that defined, let's go ahead and try to find what we need here, okay? So we already know what the weight density is. So the weight density is going to be 62.4 pounds per cubic foot. We got that, okay? So we got this here. Now for our strip depth, we know that our strip depth here, whatever height this is going to be is h, but in general, and let me erase this here to kind of make this a little bit more clear. In general, we know that the height of the water at the point where we need to stop, which is when we have this 5,000 pounds of a force here, that's going to be some constant value, okay? Now, of course, height can go anywhere in between 0 to 11 feet based upon the dimensions of the trough here. But we don't know exactly what that value is going to be, okay? So at best, what we can do to make life easy for ourselves is to say, all right, well, if this is going to be some certain height, then we can make that strip depth be height minus y. Now, you may be wondering, why are we using h minus y instead of just h or just y? Okay, so I'm going to go ahead and explain that now. So remember that this strip depth here, what it's doing is actually a part of what we need to use to be able to model the pressure that is actually being applied on these end plates, okay? And based upon the actual height of the water, you're going to have the pressure is going to be a little different, okay? So my point here is this. If we let y equal h, in other words, this y value that we find is the same as this value h here. And again, that's one of the things that we need to find out. And we're going to find that out since we know this. But whatever that ends up being, if I fill up the water trough up to that amount, then of course, right at the top of the water here, the fluid force right here at the top should be 0, okay? So it shouldn't be hardly any force at all. However, if I let y equal 0 here, then I'm not just considering this. What I'm actually considering is all of this. And so what I'm doing there is I'm considering the pressure of the whole entire plate at that point. Because again, if y is equal to 0 here, then h minus 0 is h. So I'm considering the pressure from the bottom of the water trough all the way to where the water stops. Okay, and so that's the reason why we need to model this as h minus y versus just h or y. So I hope that makes sense. All right, so now let's figure out what this length of the horizontal strip is going to be. We know it's going to be 2 times x. It's just going to be x here, and so to do that, we just take this equation here, which is modeling the right-hand side of this end plate, and we're going to solve it for x. And of course, if we do that, we see that x is just going to be 6 over 11 times y. So of course, that means 2 times x is just going to be 2 times that, which is going to be 12 over 11 y. Okay. So to say all that, we know here that L of y is going to be 12 over 11 times y. And of course, we'll leave dy to being dy. So now that we have all that, we can now find out, we can go ahead and apply everything to this formula here. So we got F is equal to, now our C and our D, notice that we're going from the bottom of the trough up to where the height stops to have this pressure here be 5,000 pounds or lower, or this force to be 5,000 pounds or lower. So since we don't know what that is in terms of y values, all we can do is go from 0 to h, okay? Because we know it can't be any higher than h. So if we put in the rest of this information, we know our weight density is going to be 62.4. We also know that our strip depth is going to be h minus y. We also know that our L of y, or our horizontal strip length, is going to be 2x, and 2x is 12 over 11 y. And then, of course, we have dy. Okay. So from this point, we also know that, I'm going to go ahead and put this in here, that this can't exceed 5,000 pounds. Okay. So I'm just going to keep it as equal to, but in reality, we would want to have that this is going to be 5,000 pounds will be less than or equal to, and then of course the integral. Okay. But I'm just going to keep it as equal to, and we know that whatever the height is, it has to be that height or lower. Okay. And that'll keep the computation a little bit more simple here. All right. So with that being said, first thing I'm going to do is all my constants I'm going to pull out. So it's going to be 62.4 times 12 over 11. And I'll have 0 to h. And what's left here will be h minus y times another y dy. Okay. All right, so this 62.4 times 12 over 11, I'm just going to keep it that way, and I'll wait to the very end to deal with that because I figure that's probably going to be some nasty decimal that I don't want to write a whole bunch of times. Okay. All right, so here I know that as far as having the rest of what's in the integrand here, I can multiply that y times both terms there, and this is going to be from 0 to h, and this is going to be This should be h times y, constant here times y minus y squared, and all that's going to be times dy. And so from that means here that we got 5,000 equals, and then again, I got the 62.4 times 12, all that over 11. And now I can just take the antiderivative of the integrand here. And so that's going to be h times y squared over 2 minus y cubed over 3. And we evaluate that from 0 to h. All right. And so from here, this basically means we have 5,000 times 11 all over 62.4 times 12. So I'm just dividing both sides by this constant right here. Yep, so dividing both sides by this constant here. And of course, when I do that, what I have left on the other side, note that I need to plug in h everywhere where I see y. So when I do this for the first time, it's going to be h times h squared, which is h cubed. That's going to be that divided by 2 minus h cubed divided by 3. And then when I plug in 0, after subtracting, I know that both terms here is just going to end up being 0. So I'm just going to put a 0 here and be done. Okay. All right. Also, since we have 2 and 3 for denominators here, I know that the least common denominator would be 6. So I would need to multiply this first term times 3. And so I'll go ahead and do that here. So we multiply this by 3. We'll multiply the second one by 2. And we will make our denominators here be common. Just 6. So I'll kind of do it like this. Okay. All right. And so, of course, what that's going to mean for me here is that I just have h cubed divided by 6 total. Okay. So now what I need to do is I need to take what I have here, equal it to what I have here, and figure out what h is going to be. All right, so I'm going to scroll up, give myself a little bit more room. So therefore, in doing this, if I multiply 6 by both sides, I have 6 times 5,000 times 11 all over 62.4 times 12. And I would end up, since that would be h cubed, I could do the cube root of that. That didn't turn out too hot. Let's try that again. So I would do the cube root of that to be able to figure out what h is. Okay. All right, so when we do that, this will be cube root of, and everything that's under the radical there will be about, 440.7051282. Yeah, 1282. So it'll be cube root of that. And of course, that would roughly get me to, if I do the cube root of all that, to be about 7.61 feet. Okay. So that means that I wouldn't be able to fill up the water in this water trough beyond 7.61 feet because anything over that would have a fluid pressure on those end plates of more than 5,000 pounds. Okay, so that is one of the first things that we needed to do. We needed to find out, well, one of the things that we needed to do, we need to find out what was the value of H. Now, the other thing that we need to find out, and I'm actually going to go back to the beginning of the question here. So it says, assuming the density of water is 62.4 pounds per cubic foot, it says how many cubic feet can a trough hold without exceeding this limitation? Okay, so now that we know what the height of the water is, and that's going to be in there, we can now figure out what the actual volume, in other words, cubic feet, what that's going to be. Okay, and by doing that, we can essentially just take the area of the triangle that's made with the height of it being 7.61. Of course, we would have to figure out what the base would be, but of course, we would know that because we already got a formula for what 2x is. And then after that, of course, this thickness here would be 30. So that's how we can actually figure out what that volume is going to be. It's just basically the area of, let me draw it right here. So it's basically just the area of this triangle here. And then of course, we would multiply that times this length of 30 feet. And that's what we would get. All right, so I'm going to call this portion here that we did, this was actually like the second question. So I'm going to call this part here, part B. Let me switch colors again. So we'll call this part B, and we're actually going to do part A now. It was just easier for us to do the second part first here. So for part A, notice that we have this triangle, and the height of this triangle is going to be 7.61 feet. Okay. We also know that the length of this is going to be 2x, but we also know 2x is just 12 over 11y. So this is just going to be 12 over 11 times 7.61 feet. And then of course, this is going to be our area. So I'll just do it like this: area times, and I'm going to erase this here. I'm going to say area times length of trough. So length of the trough. And of course, the length of the trough is 30 feet. Okay. So now that we have all that, area here is going to be 1/2 times the base, which is going to be this 12 over 11 times 7.61 times the height, which is 7.61 times length of the trough, which is 30. Of course, when we get that, we are going to get cubic feet here, because of course, this portion here will be square feet, and this portion here, will be feet. And actually kind of got that drawn wrong. It's more so like this. So this part will be the feet, and this portion will be the square feet. All right, so once we calculate all of that, we're going to get roughly It's not the exact value, but we're going to get roughly about 947 cubic feet. Okay. And that's me rounding down because, again, we don't want to round up to 948 because that would actually put us over where we need to be height-wise, and it'll put us over pressure-wise, so over that 5,000 pounds. Okay, so this is the second part of this particular problem. Now, again, the main thing here is that we modeled what was called fluid force, sort of similar to the same way that we modeled work. And so we kind of used what we knew about pressure being force over a certain area or force per area, and just using that to kind of build what it is that we needed. And so from that, we actually saw that there was a nice ready-made formula for us, but we kind of went through sort of the informal theory behind what was needed for us to be able to use this formula and understand it. Okay. All right. So I have one more example that I want to do here, and then afterwards, this video will be complete. So let's go ahead and hop to it. All right. So for this last example here, we have a mountain climber that is about to haul up a 60 meters length of hanging rope. So basically 60 feet of 60 meters in this case of rope is hanging down, let's say off a cliff or something, and this person has to pull it up. Now we want to know how much work it will take if the rope weighs about 0.75 of a Newton per meter. Okay. So I'm going to draw a visual here so that we can kind of see what's going on, and hopefully this will help us to be able to model our situation here. Okay. And let's just going to put our ground right here. And so this will be our ground right here. And we're going to say this is some tower or building or whatever. And this is going to be the person, but we'll move them a little bit closer since they actually have to pull something. So we'll put them more so right here. Okay. And let's use a blue rope, and let's say this rope kind of looks like this. It's hanging all the way down to the ground here. And we know that this total length, I'm going to use this color here. So this total length here is 60 meters from the ground to the top there. And we know that this rope weighs, we're given the, the weight in newtons per meter. So we'll just express it that way. So weight rope is this. Okay. And so in a way, this is like the weight. Can't really call it density, but that's the closest thing to it. So it's like one-dimensional density for the rope. Okay, so it's like the weight density in one dimension for it. So again, we want to know how much work will it take to pull up the rope. Okay, well, this is what we do know so far. Okay, now we know that when we're at 0 feet, okay, in other words, the person here, they've pulled up 0 feet of rope. okay? So when x is 0 feet, and we're going to define x as amount of rope hauled, and that's going to be in meters here. And I don't know why I keep on putting feet when this is in meters. All right, so this is in meters here. Then we know there that the rope is going to pretty much be at its heaviest. So the weight of the rope is just going to be 0.75 newtons per meter. And since all 60 meters of it is hanging, then it's just going to be 0.75 times 60, which is 75% of 60 meters. And of course, the meters units are going to reduce to 1, so this is just going to end up being 45 newtons here. Now, when we do the same thing, when he's pulled up all 60 meters of the rope, then the weight of the rope, of course, is going to be 0. And I'll go ahead and formally write it out. But here we have 0 feet that's hanging, so we got 0 newtons. Okay. Now, we say that because as the person pulls up the rope, the thing that we know is that the weight of the rope is decreasing. So, and since it's going to be decreasing for every meter that he pulls up or she pulls up, then we know that it's going to be decreasing at a constant rate, which means that the weight, the way in which we can model the weight is going to be linear. Okay. So here I'm going to let weight be my force function. I'm just going to call it f of x here. And we know that this is going to be modeled by a linear function. And where here we're just going to do the rise over the run. And so if we look here, we know that we have a point 0, 45 on the graph of our line, and we have the point 60, 0 on our line. Okay, so the change in y values, we go from, we'll say the weight being 45 to the weight being 0. Okay, and the distance of the rope that's hanging from 0 to 60. Well, from 60 to 0, I should say. Yep. Okay. All right. So now that we have that, of course, this is just going to be 45 over minus 60. And this is going to be the same as 3 over 4. And that's where this 0.75 newtons per meter comes from. Okay. So I did that just to show you that that's where that's coming from. So we have this rate here. So now that we know that we have this particular rate, then of course my force function here can be simply modeled as a minus 0.75x plus, and since by definition this is a y-intercept, I can make that be 45. Okay. All right, so I got rid of that last line at the bottom since we had modeled our force function or our weight function with the linear function up here, the 0.75x plus 45. But I did want to make sure that you realize that this rate, since the weight will be decreasing as more of the rope gets pulled up, that rate in this model would have to be negative here. So I want to make sure I mention that. All right, so to wrap this up now, we know that work, because that's the thing that we're trying to find, work is going to be force times distance, okay? Now, the thing is we have our force function. And so this is one of those situations where we can actually just say work is going to be the integral of our force function from lowest x value, which is going to be 0, to the highest, which is 60. We could do that in this instance because of the fact that here we have our force totally modeled, and the only thing that we're doing now is applying this force that is basically at a constant rate here over this distance of 60 meters. Okay, so in a situation like this, we could use this formula for work directly. So in doing that, we know that our force function here, again, is just linear. Okay, it's just linear. And so now what we can do is essentially just take the antiderivative and figure out what the answer is. So we'll say this is 0.75 x squared over 2 minus 0.45x, and that will be evaluated from 0 to 60, and this will be a -3 over 4. I'm going to change that to a fraction there. See if I can do some reducing. So we have that minus 45 times 60. And that's all in the first one. And this should be a plus, not a minus. There should be a plus there. And then in the second one, it's going to be 0 in both terms. So I'm just going to write 0 there. Okay. All right. And so from here, if we work this all out, this will be 3 over 4, 60 times 60 over 2 plus 45 times 60. And 60 divided by 2 is going to give me 30. 60 divided by 4 will give me 15. And here we have 30 times 15. That will be 450. And so 450 times 3 will be 1350. So it's going to be a minus 1350 there. Plus, we have 45 times 60, which is 2700. And of course, if I take 2700, subtract 1350 from it, I'm going to get 1350 because it's half. And since this is work and we were in international units, this will be Newton meters. Okay, and so that will be how much work it takes, or Newton meters, or we can say joules. Yeah. So it'll be 1,350 joules. So that's how much work it'll take for this person to haul up that rope. All right. So with that being said, this concludes the second part of this video, a video series on work. Again, I know that this video was long, but I wanted to try to get in a lot of different examples because based upon what textbook you're studying, what kind of problems you're dealing with, I've pretty much used all the examples that I have for what I've seen as far as students studying a course like this and the type of problems that they have to deal with. So hopefully the problems that I covered here in both of these videos covered what you needed for the course that you're taking. All right, so I'll see you in the next video. Take care.